my question to you folks. Question number 3. What do you notice about your answers to warm-up questions 1 and 2? They're the same, yeah. So what's interesting about this is, you know, I know we don't really write this like ever, but you folks recall that when we take the square root of 4, there is an index in that radical. The root you actually end up taking is 2. So when you take the square root of 4, that's actually the same as raising 4 to the 1/2 power. All right, now let's see here. Number 6. What do you notice about your answers to questions 4 and 5? What is it, John? Oh, yeah, they're the same. So what's interesting is that you're noticing that taking the cube root of 8 is the same as raising 8 to the 1/3 power. So now let's see if we can broaden that to draw a conclusion. In number 7, we're supposed to draw a conclusion about rational exponents and their relationship to radicals. What do you think? Go ahead, Chris. Nice. I'm just going to focus on the first thing that you said. The denominator of the rational exponent or fractional exponent is actually equal to the root, or, you know, some of you like to call it the index of your radical. I'm going to talk about your second fun fact in a minute there, Chris. So, but yeah, as far as this warm-up is concerned, do you see that? Because if you see that, you literally taught yourself half of today's lesson. You actually taught yourself a definition, which is pretty cool. Questions about that? So the bottom number is the root. All right, so let's explore this idea a little more. I think there's a little piece of my screen missing here. And the first part is supposed to say, I think, in nice big bold letters, it says rational exponents with a numerator equal to 1. So more or less what this is if you have a raised to the 1 over n power, n being some number that's not 0, that's actually the same as taking the nth root of a to the first, but we never really write that one there. A to the first, it's just a, so we don't need that really anymore. So we could apply this now, you know, prior to walking in the door today, 16 to the 1/2 power, that's the same now as the square root of 16. Walking in the door today, you were like, how do you even do that? But now we know that a fractional exponent is actually the same as a radical. Fractional exponents are radicals in disguise. That's the big idea for today's lesson. This little 2 right here is actually our index or our root for our radical, so works out. Square root of 16 then is a lot easier to work with, you know. Square root of 16 is just 4. If we move into part B, I notice the denominator is 3, which means that I have to take the cube root of 32. And then you have to ask yourself, what's the perfect cube factor that goes into 32? 8. Cube root each piece. And this is me using my product property of radicals to simplify the cube root of 32. The cube root of 8 is 2. And I can't take the cube root of 4. There are no perfect cube factors of 4. So I get 2 cube roots of 4 as my answer there. So out of this, I'm hoping that you start to see there's a 2-step approach to doing these problems. Do you see it? Step 1, you write it as a radical. Step 2, you simplify the radical. That's what we're doing. So if we look at part C, you're like, oh man, a negative exponent. And you might remember from earlier chapters, you can't have a negative exponent in an answer. We're going to go over more of these properties of exponents tomorrow, but the rule that this is asking you to remember right now is sort of our upstairs downstairs rule. If you'll recall, if we have a negative exponent, it's kind of like that whole thing just moves to the bottom of the fraction. And you can't have a topless fraction, right? It's not decent, it's inappropriate. We put a placeholder there of 1. So you have 1 over 108 to the 1/3 power. So now we would go ahead and execute our two-step approach. This is now the cube root of 108 on the bottom of our fraction. And the perfect cube factor that goes into 108, 27, goes in 4 times. Cube root each piece. On the bottom, you have 3 cube roots of 4. So to finish up this particular answer, you could just say that this is equal to 1 over 3 cube roots of 4. And I know some of you are probably sitting there squirming a little bit because you have a radical in the bottom of a fraction. I didn't teach you how to rationalize when there's a cube root on the bottom of a fraction. You're only responsible for rationalizing the denominator when there's a square root down there. So if there's a cube root down there, you don't have to worry about it. It's a little messy. You're welcome. Part D. Now we have letters in it. What you're going to notice, and you're going to want to write this down, see how x is raised to the 1/3 power? The 13 is not. The 13 is actually only raised to the 1st power. So please understand that 13x to the 1/3 is not the same as 13x all raised to the 1/3 power. So the only thing that has the fractional or rational exponent here is the x. So 13, that's just 13. X to the 1/3 power, we're learning that that is the same as the cube root of x. That's it. You can't even simplify it anymore. The end. Questions about that? Okay, so now I'm going to go on to the thing that Chris mentioned a little earlier. I didn't know if you heard him or not, but he did have 2 parts to his response for the warm-up. And he basically gave me this definition right here. We have to talk about rational exponents with n in the numerator. In other words, another number other than 1 in your numerator. Now, this is a little taboo, but I'm going to use e, not as a number, but as a variable, because I teach this rule as the ER rule. Now, you folks from Algebra 2 know that e is actually equal to a number. Does anybody remember what it is? 2.72, yeah, it was the natural base for the natural base logarithm or whatever. Yes, the base for the natural logarithm, sorry. Rational exponents with n in the numerator, I'm going to teach this to you as the ER rule. So here's how this works. If we have a being any number, and you raise it to the e over r, over r, we get this ER rule. So what do E and R stand for? What I need you to take away from today's lesson is the fact that that bottom number right there, that R value, that guy, is always going to be our root. So the denominator is always your root. The numerator, I call it the ER rule, that top number is always, E is for exponent. E is for exponent. So you could put that E in 2 places. You could put that E right next to your A to keep it company, A to the E's power. Now, E is not 2.72. It's just a letter that the word exponent begins with. So I chose E there. You could also write that in a slightly different way. Feels a little long there. The rth root of A could be underneath a set of parentheses there. And then we could bounce that E outside of a set of parentheses. This version of the rule is super helpful when you don't have a calculator. And you want to keep your hands off your calculator as much as possible. So, again, it's still a two-step process anytime you look at one of these problems. The first thing you do is you write it as a radical, and then you simplify that radical. So I'm going to apply both definitions for a to the e over r. You're going to see the case where sometimes one works better than the other. So if I have 4 to the 3/2 power, please understand that you could rewrite that in two different ways. But step one is to rewrite it with a radical instead. You could rewrite this as the square root of 4 to the 3rd power, or you could rewrite it as the square root of 4 cubed. You could do it either way you like. It's up to you. It'll work out to be the same answer both times. 4 cubed, that's 64. The square root of 64, that's just 8. If I do the square root of 4 and then cube it, I still get the same answer. The square root of 4 is 2. Bring down my cube. 2 to the 3rd power is also 8. So really it's up to you. You don't have to do both ways. Just pick one. Whichever way you like better. You're going to see that in part B, I'm going to set it up twice, but really one is definitely more practical than the other if I'm not allowed to use a calculator. So what you're going to see here is we have -8, and we could take that cube root and raise the -8 to the 4th power. But I don't have a calculator, do you see? No calculator in my hand. So I don't know what -8 to the 4th power is off the top of my head, and I don't have a calculator in my hand. So setting it up in this way, I'm like, oh, I don't know what 8 to the 4th is, so I'm going to get rid of that. I'll use the other way. It's a little friendlier if I don't have a calculator in my hand. Check it out. I could set this up as the cube root of just -8, and then raise all that to the 4th power. Cube root of -8? Oh, I know what that is, because the cube root of 8 is 2. The cube root of 8 is 2. The cube root of -8 is -2. Raise it to the 4th power. And then I know what 2 times 2 times 2 times 2 is. That's just 16. So -2 all raised to the 4th power would be a positive 16. So you see how the second definition of a to the e over r actually worked out a little nicer, but you could use either definition. Part C. We have 27 over 8 all raised to the 2/3 power. Again, it's a two-step algorithm, two-step method. You write it as a radical, and then you simplify. I noticed that 27 and 8, those are 2 of the 5 famous numbers you had to memorize as perfect cubes. So I'm actually going to use that second definition right away. I'm going to rewrite this as the cube root of 27 over 8 and raise all of that to the 2nd power. That's me using my ER rule. Do you see again how the denominator is my root and the numerator up here is my exponent? Cube root of 27 over 8, that's not bad. Cube root of 27, that's 3. The cube root of 8, that's 2. And I was able to do that because I applied the quotient property for radicals that we talked about in the first part of the chapter. And then I square this. Means I have to square the top, square the bottom by our power of a quotient rule. So that'll be 9 over 4. Questions about that? Last part of the lesson is, again, I have to put letters to it. This is an algebra class, right? We do things with variables quite often. So you see we have x to the 4/3. The 2 steps are still the same, by the way. You're going to write it as a radical, and then you simplify it. Although you folks know that when you simplify with letters, it's usually a little bit of a different process. So if I write x to the 4/3 as a radical, that's the same thing as the cube root of x to the 4th, which you could simplify. Do you remember how to simplify this? Do you, Chris? Yeah, you got to ask yourself, how many times does 3 go into 4? 3 goes into 4 one time. And there's 1 left over underneath. Part E, I'm going to rewrite that as a radical. So it's the cube root of 2x to the 5th. Once again, I'm going to use my division. 3 goes into 5 one time. So 2x to the 1st comes out. And then there are 2 left over underneath. You could simplify a little bit underneath there. So you get 2x times the cube root of 4x squared. And then the last example of the day, and then we'll talk about your homework. We have 2 times y to the 3/4 times z to the 1/4. Again, the first step is to write it as a radical. The 2 doesn't have an exponent attached to it. We can assume that that's 2 to the 1st power. So to rewrite that as a radical, 2 to the 1st power, it's just 2. Y to the 3/4 is the same as the 4th root of y to the 3rd. And then z to the 1/4 power, that's the same as the 4th root of z to the 1st. Can't simplify either of those radicals, but what I do notice is that their indices are the same, which means we can use our product property to glue those things back together. So this is actually 2 times the 4th root of y cubed z to the 1st. So that is that. Great. So take a look over that because that is our lesson for today. Questions about it? You ready to practice? What's up? Yeah, my smart board broke last period. Oh, that's fun. Good times. Questions about that?